important. It's called the fundamental theorem of algebra, which might be a problem. What Gauss is telling us here is that there are two perfectly good values of x that we could plug into our function and get 0 out. Where could these two missing roots be? The short answer here is that we don't have enough numbers. We typically think of numbers existing on a one-dimensional continuum, the number line. All our friends are here. 0, 1, negative numbers, fractions, and even irrational numbers like root 2 show up. But this system is incomplete. And our missing numbers are not just further left or right. They live in a whole new dimension. Algebraically, this new dimension has everything to do with a problem that was considered impossible for over 2,000 years. The square root of negative 1. When we include this missing dimension in our analysis, our problem gets way more interesting. Now that our input numbers are in their full two-dimensional form, we can see how our function x squared plus 1 really behaves. Our function does cross the x-axis. We were just looking in the wrong dimension. So why is this extra dimension that numbers possess not common knowledge? Part of the reason is that it has been given a terrible, terrible name. A name that suggests that these numbers aren't even real. In fact, Gauss himself had something to say about this naming convention. So yes, our missing dimension is comprised of numbers that have been given the ridiculous name imaginary. Gauss proposed these numbers should instead be given the name lateral. So from here on, let's let lateral mean imaginary. To get a better handle on imaginary, I mean lateral numbers, and really understand what's going on here, let's spend a little more time thinking about numbers themselves. Early humans really only had use for the natural numbers, that is 1, 2, 3, and so on. This makes sense because of how numbers were used. So to early humans, the number line would have just been a series of dots. As civilizations advanced, people needed answers to more sophisticated math questions, like when to plant seeds, how to divide land, and how to keep track of financial transactions. The natural numbers just weren't cutting it anymore, so the Egyptians innovated and developed a new high-tech solution, fractions. Fractions filled the gaps in our number line and were basically cutting-edge technology for a couple thousand years. The next big innovations to hit the number line were the numbers 0 and negative numbers, but it took some time to get everyone on board. Since it's not obvious what these numbers mean or how they fit into the real world, 0 and negative numbers were met with skepticism and largely avoided or ignored. Some cultures were more suspicious than others, depending largely on how people viewed the connection between mathematics and reality. And this is not all ancient history. Just a few centuries ago, mathematicians would intentionally move terms around to avoid having negatives show up in their equations. Suspicion of 0 and negative numbers did eventually fade, partially because negatives are useful for expressing concepts like debt, but mostly just because negatives kept sneaking into mathematics. It turns out there's a whole lot of math you just can't do if you don't allow negative numbers to play. Without negatives, simple algebra problems like x plus 3 equals 2 have no answer. Before negatives were accepted, this problem would have had no solution, just like we thought our original problem had no solution. The thing is, it's not crazy or weird to think these problems have no solutions. In words, this algebra problem basically says, if I have 2 things and I take away 3, how many things do I have left? It's not surprising that most people who have lived on our planet would be suspicious of questions like this. These problems don't make much sense. Even the brilliant mathematicians of the 18th century, such as Euler, didn't really know what to do with negatives. He at one point wrote that negatives were greater than infinity. So it's fair to say that negative and imaginary numbers raise lots of very good, very valid questions. Like, why do we require students to understand and work with numbers that eluded the greatest mathematical minds for thousands of years? Why did we even come to accept negative and imaginary numbers in the first place when they don't really seem to be connected to anything in the real world? And how do these extra numbers help us explain the missing solutions to our problem? Next time, we'll begin to address these questions by going way back to the discovery of imaginary numbers.
Enjoy the video?
Yes.
One of the work I'll give you is the history of numbers. Anyway, before that, These are two guys trying to, make fun of each other. So think of these people as maybe Damien and who you make fun of in the class?
Brandy.
Brand. So
Well, it's probably negative thing.
maybe Brand is trying to talk him out on something and he's not being reasonable. Then let's say Brandy said, oh dude, be rational. Then he's trying to tell Brandy, get real. Basically, this is just some kind of crazy math joke. We all know that pi is not a rational number, right? And what we are trying to learn today is the concept of I, which some of you probably come across already, which is why somebody was trying to tell me maybe square root of something is something. I'm going to put that there so we can remember Brandon and Damien as we walk through this chapter.
I don't get the part where it became three-dimensional.
You don't get it?
Yeah. He literally put it up and...
It's called video editing and
Yeah, I know that.
He's just trying to tell us there's another dimension that we are not looking at. So some of you, when you plotted the last graph, it didn't touch the x-axis, isn't it?
Yes.
So you claim that there is no solution.
Yes.
Want to go up? Okay. You claim that there is no solution. So what that video is trying to tell you is that there is actually solution. You're looking for, your solution is always from your investigation, is where it crosses the axis, right? But it's actually, you're looking at the wrong place. The solution crosses some axis, but not the axis you're looking at. That's what it's trying to show you in that video. Okay? That imaginary axis with the real axis is what we need to discuss complex numbers, which we are beginning now. Okay? I can share this video and this series with you later. You might find it helpful in the project I'm going to be giving you. You can have, I'll give you all the details later. You may present your work in form of a video. It doesn't have to be like a poster like some people do. And so that we can all see what we have learned about complex numbers. Okay, so let's bring out our notebooks and textbooks. It's actually on chapter 14. Yes, please. Student 18. we do complex number last year? Yes, no? Now, this is one of the very important topics you need not only for IB but for the future. Of course, you investigate that yourself as part of the project. I'll be asking you to also indicate in your project everything you can tell us about complex number as well as the usefulness of complex number. Okay? I think I would rather put in groups so it's not individual person coming for presentation. That's like 12 different presentations. So do we prefer groups of 2 or 3?
3.
Group of 3? Okay, it will be random. When Lillian comes, we'll do random picking. So I will come with papers 1, 2, 3, 1, 2, 3. Whatever paper you pick, that's your group. If I ask you to pick a group, you probably want to go with your best friend or your greatest enemy. And we don't want to cause World War X, something like that. So, due to the time, we'll be focusing on, if possible, up to these 3. Then when we come tomorrow, we'll proceed from here. After the modulus and argument, of course, we should be able to move to some properties. There will be some proofs. This topic, I needed to take it more seriously because you also need it when we get to some advanced topics. You will always come back to complex number. Anyway, so let's begin with what complex numbers are. Because for us to understand what to watch in that video, we need to know what exactly are we dealing with. Okay? I'll just do a little summary as to buttress the points raised in the video. Back in the days, of course, none of us was here. We had natural numbers. Some people call it counting numbers. I want to believe it's called natural numbers because it comes to us naturally. Nobody talks about 0 when you are young. Everybody begins to count from 1, correct? None of us here started counting from 0. When you started counting numbers, it is always 1. 1, 2, 3, then they introduce 0 to you when you master 9. And they tell you 1 and 0 is 10. 1 and 1 is 11. And that's how you develop that. So natural numbers are counting numbers. Also, if you want to count how many books or whatever, people hardly do not mention 0. And you could see that even the concept of 0 and negative were even rejected by some people. I was once obsessed with history of numbers, and to the point that I was investigating pies and zeros and even factorials at the point. And one of the things that I come across then, can't remember vividly, was that the first person that mentioned either 0 or negative number was actually killed. Yeah, for even it's like coming to a society and mentioning something that is a taboo. You get the point? It's like going to the US or UK today and say, oh, you need to kill the LGBT. You might go to prison for life for that. Because that is not their belief in that society. Or if you go to Africa today, some African countries, or even the Middle Eastern countries, and tell them if you don't allow the LGBT, you are wrong, or something like that. That's not what they believe in. They might even jail you in Saudi Arabia for being a gay or lesbian if you are not killed. They are very strict with those things. So imagine such a society, you are saying something that is anti their society. That was how those notions were viewed in those days. How dare you mention 0 or negative? I don't know if 0 was the first word that was used anyway. And somebody paid for his or her life. I think it was a woman at Haiti or something. Because I remember we named a competition after her in Nigeria. Myself and some colleagues from another school, we come up with a math challenge. We call it a Apecia Math Challenge. A female, very brilliant mathematician, I believe. I think she was a very beautiful woman as well. She killed her. Anyway, now, when some problems like the Apple problem you saw were not solvable, then there was need for us to have more symbols and numbers to represent some of these things. I'll give you a scenario. We operate a bank. Krista deposited maybe 7, whatever the currency is. And let's say Brandy deposited 4 of whatever the currency is. So Krista comes to withdraw 3 out of our money, or let's say 4, let's say 5. Okay? So our balance should be 2, right? So Damien, very good customer of ours, says, oh, I need more than what I have in the account. Can you give me some extra money? I'll pay you back once my salary comes in. Getting a loan from the bank. And Damien says, I need about 6 just to settle stuff. Okay? So as at then, we will also note that Damien is owing us 2. Right? But if there are thousands of Damien, you don't know which of them is owing you 2 and which of them actually is having 2 as his money in your account. So there is need to use symbols like minus to represent, oh, this is actually a debt. This is actually something that he has in his account. But imagine how you would have represented this situation, or you could have denied him the loan and said, sorry, you have to always get only what you have, rather than do something called overdraft. Overdraft is when you get more than what you're supposed to get from the bank. Okay, and you pay them in form of a loan or whatever. So there was need to introduce more symbols, which is 0 and the negatives. And the combination of what you have so far gives you the z instead of integers, the integers. Okay? Then later, you can't tell anybody, oh, can you divide maybe 3 oranges into 2 for people? Of course, it should be 1.5 because we know that now. 1 orange, then divide 1 in half, right? But back in the days, there was no representation for decimals or fractions. Then there is need for more numbers to come in, and that is how we extended everything into the set of real numbers. And even that failed in that situation, the last question that you did. Problems like x squared equals negative 16 were not, well, this we don't look at the problem. This will actually be the original problem. X squared plus 16 is equal to 0. How do we solve this equation? Then they discovered, oh, we don't have enough numbers to take care of these problems. Then that was how the complex numbers were introduced. So basically, the complex number looks like the largest of them all, isn't it? Okay. We use this symbol to represent a set of complex numbers, like a script. This is for real numbers, integers, natural numbers. We have irrational numbers, Q, okay, and so on and so forth. So complex numbers, please write. They are always of the form a plus ib or a plus bi, as the case may be. Maybe I put the I right in front of B because that's how we'll be writing it. A plus bi, where a and b are real numbers. So for example, we can have 2 plus 3i. You can have minus 4i. This means 0 minus 4i, isn't it? It means the first part is 0. Get that? Can we have ordinary 3 and call it a complex number as well?
Yes.
Yes, it means the imaginary part does not exist. Which means this is like 3 plus 0i, something like that. So these are can you check if we are recording this class? The symbol.
Yeah, it's recording.
Thank you.
Just that.
This is uppercase C, please.
Parents had us. That's okay.
That's okay. Maybe I'll move to this one. To avoid
The blue part, they can see.
Okay. So I won't go beyond this point now. because of carrying n. So this symbol represents the set of complex numbers. Okay? So if we say K belongs to that, then K has to be in the form A plus BI. That's what we're saying. Okay? That symbol represents the set of complex numbers. I forgot to mention what I represent. I represent the square root of minus 1. Or better still, you say I squared is equal to negative 1. That is the imaginary. That determines the imaginary part. That is the representation of I, square root of negative 1. So which is why if you want to solve the square root of this, it's like the square root of minus 1 times 16. And using your knowledge of surd, square root of 1 times square root of 16. This is I and this is 4. So that's why your calculator will show you 4I because of this. Sorry, I just assumed everybody knew that part, so that's why I didn't mention it. So now you know what it is. Okay, now having said that, I should have added that at the beginning, so apologies. So I represent the square root of negative 1. That is, now with this definition, we are able to now work with complex numbers because we are able to represent the square root of negative 1 as another symbol on its own. Okay? The first thing I want us to look at is how do we represent this in a geometric form. After that, before then, let's consider what happens to the powers of I. Okay, also, the real part of K. When I say in this case, I'm talking about this. Okay? The real part of K equals A plus BI. And B is called the imaginary part. Imaginary part. Okay? So we have the real part and the imaginary part. Two parts make the complex number. So if A is 0, then the number is strictly imaginary. And if B is 0, then the number is real. Does it make sense? Does this make sense? Can I ask you to investigate this. You know this, right? Yes? Let's see what happens to 3, 4, 5. No calculator, please. And maybe we can make a conclusion. Quickly. Write down, please. Not look at it and tell me the answer. Write down. It's an investigation, so and it's part of the notes. Where did you get square roots, Mr. E? Does anybody get something here? Height 3? I said no calculator. You're pressing the calculator. I just said it. Did anybody get anything here? What did you say? Close? Negative what? Leave it in terms of I or something. You don't have to go to, I don't want to see square root, please. Negative, what is 1i? Come on. Yeah, speak like Form 5, not babies downstairs, not upstairs. So basically this is I squared times I, right? And what is I squared? Minus 1 times I, so this is negative I. So what about power 4? 1, that's correct. Power 5. I'm sure you're not writing it. And that is what I told you not to do. Don't just guess and say the answer. I want it written in your notebook. When you get to 8, let me know what you think. Come on quickly. We have about 12 minutes to lunch. Kind of hungry I am. You done? Up to 8. Are you up to 8? I didn't see how you worked it out. I need to see how you worked it out. I just said there is no square root. I can see you writing square root again. There is no square root. You just erase square root of minus 1. I've just done an example.
This time this is not 2i.
Treat I as algebra, and of course, include your knowledge of definition of I now. Okay, I'll go one more step. Maybe that's going to help some people. This is just I cubed times I. Yes? I cubed is minus I times I. And that is minus I squared, which is minus 1, which is 1. If I don't want to do that, I to the power 4 is I squared times I squared.